Well, good morning, everyone. We are going to work through, hopefully get finished today, centres of mass. I'm sure we will actually, and then we can get, if we have time at least, we'll start the last part of 8.3, which is the hydrostatic pressures. So, the kind of questions we're going to tackle today are: how do you find centre of mass when the area of interest is between two curves, typically f of x and g of x? Well, the x coordinate of the centre of mass is given by this, and the y coordinate is given by this. So I'm going to start off with which one? Yeah, this one here. I get a feeling I may have done this question. Does it look familiar or not? If it doesn't, then I'll keep going. Looks good, okay. Now, if you look at this, the information's not really given in a very clear or particular way. Y equals x squared is good. It's that guy. And if I want to sketch this guy, I really have to think of it like that. And now I can see who they're talking about. And so the region that we are going to find the centre of mass of is that region there. And if you set these equal to each other, it's not difficult. Can you trust me that that's at 1? It's pretty obvious it is. So if I was looking at this shape and I was trying to decide where my centre of mass is, I'd probably put it round about there. Does that seem reasonable? So let's find out what it is then. It's x bar is the integral from 0 to 1 of x. This fella is higher than this, so it's actually the square of x, take away x squared. That's going to be the integral from 0 to 1. Turn that into x to the half, and then distribute the x. You know, get that? Yes.
So from yesterday, I have
1 over a?
Yeah, 1 over a.
Thank you. I'm getting old. So, oh, that means I still have to find a then, don't I? Should do things in order. So a is going to be the integral from 0 to 1 of the square root guy, take away the x squared guy, dx. That's going to become x to the half. And that's going to be 3/2, 2/3, 1/3 x cubed, 0 and 1. That's going to get you 2/3, take away 1/3, minus nothing. Oh, 1/3. So, double check, add 1 to power, divide, add 1 to power to divide, 2, yep, okay, we're good. So I can now return to this fella, and 1 over the area is 1 over 1/3, and 1 over 1/3 is 3. Cool with that? 1 divided by a third. Now add 1 to the power. Divide by the new power. Add 1 to the power. Divide by the new power. And you're looking at 3. 2/5, take away 1/4, minus nothing. That's going to be 8/20. That's going to be 5/20. So that's 3/20. That's going to come out, I believe, as 9/20. We cool on that one?
Excuse me, Professor.
Yes.
Leah's trying to get into the class.
Oh, thank you. Yeah. Thank you for doing that. Do that again if I forget, because I get too caught up in what I'm watching, and I've got all these little windows that get in the way. Our cool with X bar is 9/20. Right. So I need to find the other one, which is Y bar. And it's 1 over A, the integral from 0 to 1. And it's basically a half. One guy squared, take away the other guy squared. And the top one and the bottom one. And 1 over A is still 3. Bring out the 2, so it's 3 halves. That guy gets you X, and this guy gets you X to the 4. Power rule. One half, take away 1/5, minus nothing. That's 5/10. Take away 2/10, that's 3/10. And the answer is 9/20. Yeah, that seems reasonable. It's in the right ballpark. There is something that I can say with a fair degree of confidence, and is that, do you notice that this shape has an axis of symmetry that goes through that line? And that line happens to have the equation y equals x. Now, if your area, the shape that you're trying to find the center of mass of, has an axis of symmetry, then the X bar, Y bar must lie on that axis. So the minute that was 9/20, I could have predicted that that was going to be the same number, only based on the fact that I could see from this shape the symmetry. Now, if one side is big and fat and the other side is skinny, then all bets are off. It is not an axis of symmetry, and you can't say anything about it. But if I had a shape that looked like this, wouldn't I be able to tell you that X bar is 0 without actually doing it? Right. I'm trying to think of a, well, you know, you can do shapes in other ways. So, can you imagine my shape was like a piece of pie? Wouldn't that be an axis of symmetry? And so I would be able to tell that X bar and Y bar were the same thing. Yeah, something like that. It doesn't mean that you won't get the answer if you do it the long way. I'm just saying that occasionally you might be able to save some work by letting symmetry take some of the heavy lifting for you. Okay, time to do an ugly one. So it's a version of 8. So A is the integral from 0 to pi upon 8. I really should sketch these guys, but if you imagine coming down this way, that's what 4 cosine looks like. And if you imagine coming up this way, that's what 4 sine 2x looks like. So this guy and this guy, and we're looking for the area between them. So it's that piece there. We go with that. Right, so cosine take away sine or sine take away cosine. What's the right order for this? If you take a, right, so if you take this one, who's the higher of the two?
Cosine.
Okay, agreed. So I'm going to do 4 cosine of 2x, take away 4 sine 2x, dx. It's going to be the integral from 0 to pi upon 8. I could pull out the 4, couldn't I? Actually, I'm not sure why I bothered with this line. Yeah, I won't bother with it. Why don't I just go straight into integrating? Okay, if you integrate a cosine, don't you get a positive sign? If you integrate a cosine of 2x, you do get a positive sine of 2x. You also get something else, times what fraction? If you integrate a cosine of 2x, you get a sine of 2x times what fraction?
1/2.
1/2. I've just done the linear shortcut method. If you don't like that, couldn't you do a u sub equals 2x and do it that way? Right. If you integrate a sine, don't you get a negative cosine? So 2 negatives make it a plus. And for the same kind of argument, you get that guy. So let's see what we get. If you plug in pi upon 8, it's 2 sine pi upon 4s plus 2 cosine pi upon 4s. Take away, if you plug in nothing, that gets you 0, and that gets you 1. So you get 0 plus 2 lots of 1, which is 2. 2 times root 2 over 2 plus 2 times root 2 over 2, take away 2. That gets your root 2, that gets you root 2. So 2 root 2 take away 2. And I don't know if it helps, but that. I would go with the A guy. So we are now going to calculate x bar. And x bar is going to be 1 over A, the integral from 0 to pi upon 8 of x times, of x times this guy take away this guy. So that's going to be what? 4 cosine x's, 4 cosine 2x's, and 4 sine 2x's dx. A is 2 lots of root 2 take away 1, 0 e pi upon 8. If you bring out the 4, it goes there. And what you're going to be left with is s cosine x take away x sine 2x dx. And this is where I'm going to pause. How am I going to integrate x cosine 2x? Because that's not a short question. What technique will I use to integrate x cosine 2x?
Integration by parts.
Right, and I'm going to make this guy f and this guy g. I suggest strongly that you do these as two separate questions, then subtract the answer. Can you imagine that's going to take about 5 minutes? So dot, 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 and it's done. Now let's look at y bar. 1 over a, the integral from 0 to pi upon 8, 1/2, the first guy squared, take away the second guy squared. This guy becomes that fella. If I pull out the half, well, let's not pull out the half quite yet. I think I can see something's going to happen. That guy is going to get you 4 cos squared 2x. And this guy's going to get you take away 16, I should have said. Sine squared 2x dx. And 1/2 times 16 gets you 8, and I'll pull out the 8. And if you pull out the 8, you're left with this fella. What's missing here is how to tackle this guy. And I keep missing the 2 x's. Don't know why I keep doing that. Right. I need to figure out how to write down cos squared 2x, take away sine squared 2x. How am I going to tackle that guy?
Double angle.
And so let me show everyone the version I'm going to use. I'm going to use the theta version. And basically, cos squared take away sine squared is the cosine of 2 angles. Now you might say, but that isn't theta. It's not even x, it's 2x. So how does that work? I want you to think of theta as a placeholder for 2x. So if you do it in that way, then the cos squared of 2x take away the sine squared of 2x will be the cosine of 4x. So if I then return to here, we have 8 over 2. Oh, no, we don't. We now have 4 over root 2 take away 1, because I cancelled a little bit. The integral from 0 to pi upon 8. And this fella is now the cosine of 4x dx. If you want to integrate the cosine of 4x, won't the answer be the sine of 4x times a quarter? And so you can finish that off. Right, so hopefully I've given you a lot of a head start on how to do that guy.
Could you show us that equation?
The double angle?
Yes.
It is.
Okay.
I'm using this trig identity and I'm just adapting it to a new situation where instead of having an x or a theta, I have a 2x or a 4x or a 10x. You could do it for anything. For instance, if I wanted to do cos squared of 5x, take away sine squared of 5x, it would be the cosine of 10x. So I want you to think of that as being the original identity, right? The mother identity. And these are its little babies. So can't you have lots of little babies using the mother as the template? I don't know if that analogy helps, but that's kind of what I'm doing, right? And you can do it with other things as well. Now, if I wrote that down with thetas, Do you recognize the double angle sine of 2 theta, right? Now, what would this guy be then, based on the same kind of strategy we used before?
Sine of 10 theta.
Well, we'll keep the letters, 10x.
Right.
Yeah.
Yep.
So you just because you have an identity doesn't mean that's the only flavor of that identity. Can't there be lots of little baby versions that you could use as well if things, you know, pop up that need them. Okay. The next question that I want to do is a version of 10. And here we have x cubed take away x. And we have x squared minus 1. And we're going to, it's going to be the area between these two guys. Now, it's not always obvious what a shape looks like or even where they intersect. So I'm going to put that into my calculator. So it's x cubed, take away an x, and then it's an x squared, take away, just check it's the right question, take away 1. And then I'm going to just do a window. I'm going to make an assumption here that somewhere between -2 and 2 is where all the good stuff happens. And then I'm going to do a zoom 0. And what I'll get to see is there's the x cubed guy, and here is the other guy. So the area I want is this kind of little banana shape in the middle. You see it? Right. And I'm assuming that this point's 1, and this is -1. So if that is the case, then I can reduce the window and zoom 0 again, so that the only bit I need to see is a little bit clearer the shape. There you go. Can you see it looks a bit like a whale? That's what I see, right? Now, do you recognize top and bottom? Isn't the top this fella, and isn't the bottom going to be that fella, right? Can you see that's x squared minus 1, that's low, high to low. When you do the area between the curves, it doesn't matter if the curve is below the x-axis or above the x-axis. Whichever is higher up is f, and the one that's lower down is g. So we've got that guy, right? So we are then going to get, we're going to get a, which is going to be the integral from -1 to 1 of f of x take away g of x dx. So it's going to be the integral from -1 to 1 of x cubed take away x, and I'm going to do a deliberate mistake here. What did I do wrong?
Forgot the parentheses.
Technically, shouldn't that be a 1? Because you're subtracting both of them, subtract x squared and subtract -1, which is why that's a +1. Now, although I could write that in order, and it probably would be good math too, I'm not going to. Power rule, power rule, power rule, and 1. Oops. And we will evaluate it there and there. So 1/4, take away 1/2, take away 1/3, add 1, subtract, still positive 1/4, still take away 1/2. This 1 turns into a plus, and this 1 at the end is a negative. I have no idea what that is. I'm not even going to attempt to do it in my head. Too much going on here. 1/4, take away 1/2, take away 1/3, add 1, subtract that guy. Subtract that guy means you add them. Subtract that guy. And subtract that guy means add them. And the whole thing ends up being 4/3. Much safer than me trying to do it in my head. And that's just to find A. We've only really scratched the surface. All I've done is found A right now. So, x bar is 1 over A, the integral from -1 to 1 of x, f of x, which is this guy, take away g of x, which gets you that, dx. Now, since A is 4/3, 1 over A gets you 3/4. Distribute. You get that? Power rule. Power rule. Power rule. Power rule. And I'm just going to say ... right? It's not hard, it's just long. Let's do y bar then. 1 over A, the integral from -1 to 1, 1/2, the first guy, which is this guy, squared, take away the second guy squared. One over A is going to get me 3/4. If I bring out that 1/2, it now becomes 3/8. Squaring that guy, you get x to the 6, take away 2x to the 4, add an x squared. If you square that guy, you get x to the 4, but you subtract them. You get -2x squared, but then you subtract them. And you get a +1, but then you subtract it. And you get that guy. If I now collect like terms, I have an x to the 6, -3x to the 4, an x squared, a 2x, and a 1. Right, can I just dot that one because it's just a whole lot of ugly powers plugged in at 1 and -1. And whatever you get will be the answer. Right. So it's really just algebra and big and ugly algebra. Nothing very elegant about that question. So I've got one last one of these to do. And it's going to be question 9. And it looks straightforward, but it's not. So I'm going to sketch it. I know what y equals x cubed looks like. I know that x add y add 2, isn't it? A line that goes something like this. And y equals 0. What line is y equals 0?
The x-axis.
And because it's the x-axis, do you see that we're actually finding the center of mass of that triangular piece? Now, before you start saying, hey, no big deal, it's going to be this guy, take away that guy. Look at a minute. If you draw a vertical line through that, there's no top guy, bottom guy. Isn't it actually two separate pieces? Curve on this side, straight line on that side. We don't like that because that really makes this very difficult. There are two approaches to this. I guess you could split it into 2 bits and do all lots of 2 bits, or you can do this. I'm going to take equation 1 and rewrite it as that. I'm going to take equation 2 and rewrite it as that. In other words, I'm going to go this away. Now, do you see that makes it a little bit easier to do, because what we're doing now is straight line to curve, right? F of it, it's not going to be f of x take away g of x, isn't it? Just going to be f of y take away g of y, right? But it's pretty much the same thing. I do need to know one key number here. I know that's 0. I need to know that number. Can I tell you it's pretty easy to find out, but it is 1. Is it? I'm saying something that may not be true. Yes, it is 1. I double checked. And that point there has coordinates 1, 1, right? So area is now going to be the integral from y equals 0 to 1. The furthest to the right is your f of y. And the one that isn't quite as far, right, is your g of y. So it's high, low when you go vertical. It's right to left when you go horizontal, right? So in this case, the straight line goes first. So that's 2 take away y minus this guy. And that's going to get me the integral from 0 to 1 of 2 take away y to the third. And that's going to get me 2y minus a half y squared. Yikes. Add 1 to the power. Divide by the new power. Evaluated at 0 and 1. That's 2 take away a half, take away 3/4, minus nothing, which is what? 3/4. Yeah, which is 3/4. Now, time is our enemy. If I'm going to do, I guess x bar and y bar are maybe a little bit disorienting, but won't I use this version of the formula to get one of the coordinates and this version of the formula to get the other? Can you tell that it's going to be very like this guy? It's just going to be lots of big, ugly polynomials, you know, half y to the 4 and 3/4 y to the 3/2 and things that look like that, right? So it's really just very messy, but I'm going to leave it at that. As far as I know, this is the only question in the homework where changing the orientation so you do it with y's instead of x's is necessary to get the answer. Do you think x bar and y bar are going to be the right way around? If I'm orientating this way? So
No, because you're it's like you turn the axes.
yeah, my x is my y and my y is my x. So see if the answer ends up being 3,2, well, you remember it's 2,3. You know, a little kink at the end that you have to fix. But I think it's worth it for that very small kink, right?
So the formulas are switched for each?
Well, that's another way of doing it. I would just keep the formula and switch the answer, which has the same effect. Right, so if that's 5 and 2, you just call it 2 and 5. So switching the formula will have the exact same effect. It's just not the way my brain works. Okay, well, our last topic. Hydrostatic forces. What we're going to do is we are going to find the total force on a metal plate submerged under the water. Evidently, engineers and people who build dams and people who build submarines and ships or stick anything near water are probably going to want to calculate what kind of total force is pushing on my dam or pushing on my submarine or whatever it should be. So let's show you the story. Imagine you've got some water, and in this water there is a plate, and for the sake of argument, this plate is very thin, so we don't care about its thickness, right? It's like a two-dimensional object. And we are interested in the total hydrostatic force. And the formula for calculating this is the integral from A to B, a guy called delta, width, depth, dx. So it's a very cryptic equation, right? It doesn't have a lot of meat on it. The best analogy, remember pulling buckets up hills, didn't you have to kind of do a force function? And it's kind of cryptic, you know, it was weight of rope plus weight of water and so on, right? The math is going to look a little bit like that in some respects. So let's try and fill in, by using this example here, what some of the numbers would be. Right, I want you to imagine that this guy from here to here is 10 meters wide. And that from here to here, it's 4 meters. And it's that. So you might get a picture, which is nice, or they might just say a 10 by 4 rectangular plate is submerged 2 meters below the surface, which is what that picture is. So far, so good. Now, you take a random slice, this little guy here, and we call that guy there, the distance from the water surface to there is going to be called the depth, and the distance from here to here is going to be called the width. And so who is delta? Delta is 9.8 times 1,000, which is 9,800. And you might be saying, where the heck does this constant come from? Well, do you know that 1 cubic meter of water, right? 1 meter by 1 meter by 1 meter has a mass of 9,800 kilograms. So delta is basically the density of a unit of water. In this case, the unit is a cubic meter, which explains why fish tanks have to be really strong. Right? You imagine a fish tank, you know, a reasonably sized fish tank. Aren't they massively heavy? You can't just put them on any old table, it'd probably crush them, right? Water is deceptively heavy. 1 cubic meter of water, right? 3 feet 3 inches, 3 feet 3 inches, 3 feet 3 inches, right? Look at how many kilograms it weighs. So that's what the delta is. The width is the width of a typical strip at a depth here. Now, in this case, I'm going to call the depth x, right? If I don't know something, I'll call it x, right? So it's now going to be the integral of 9,800. What's the width of that strip? What's the distance from there to there? 10. In fact, isn't it 10 no matter where I put the strip? This is the easiest hydrostatic force question because the strip is a fixed number. It's 10 in this case. But can you imagine when it starts becoming triangles? The strip's going to depend on what the depth is. Why is that important? Well, do you know that the pressure on the bottom of that plate is more than the pressure on the top? Because the deeper down you are, isn't there more water pressure on you? So it is important that we factor that in. Now the depth was called x, dx. So now I need to know who A and B are. Now A is where does the shape start in this case, and B is where does it finish. Well, would you agree that this shape starts at 2 and finishes at 6? Are you happy where the 2 and the 6 came from? The depth at 2 to the depth at 6. So couldn't I bring this plate and move it down much lower? And if I moved it down much lower, wouldn't these be the only two things that would change? Maybe it's from a depth of 20 to a depth of 24, right? 20 to 24. So these aren't arbitrary, right? These depend on the story as well. Now you put this whole package together, I would do this. There's going to be an ugly delta, right? It's at least going to be 9,800. But if there's other numbers involved as there were here, it could be even bigger. Suck that guy out of the integral, because isn't he just going to make your calculations really awkward if you left them inside the integral? So just suck anything that's a number out the road. Now that gets me 98,000 power rule and we now have, good grief, 1/2 times 6 squared, take a half times 2 squared, okay. 36 to 18, 4 take away 2, 16. 98,000 times 16, that I can do in the calculator. 98, 1, 2, 3, times 16. The answer is 156,800. And these units are massive. Don't quote me on this because I'll probably get it wrong. But I believe that the units here are Newton meters. I don't care if they're not, but I think they're Newton meters. Are we good? Hydrostatic forces. Question, Megan.
Oh, I was just gonna say, I think you're right, because you've got, I'd have to go through and see if all your dimensions cancel, because it might end up actually being like Newton meters cubed, which would be gross.
Or squared or some weird thing, right? So
Yeah.
don't quote me on that. You might tell us tomorrow when you have time. Yeah, I did one with the unit, dimensional analysis.
I feel
Oh,
like
wait a
it
minute, I
would be
can do it.
Newton meters squared, right? Because you have, because you could also do it with PSI. That'd be pounds per square inch. Because it's an area. It's a
Yeah,
force over an
It's
area.
an area. Newton meters squared, you convinced me. Because the example that I haven't done is one where feet. And when you do it feet, it's newtons per square foot. Or pounds, I should say, per square foot. So what's the change in this story? Can you imagine all of these things said feet instead of meters? Everything here would look pretty much the same. There's one difference. 62.5. 62.5 is the delta that you use when the units are in feet. And 62.5 is 62.5 pounds for a square foot of water, a cubic foot of water. So you can imagine taking a cubic foot of water, I believe it's 62.5 pounds.